Hello everyone, this is my chemistry video on chapter 5, which is about electron configurations. I'll be doing the level 4 assignment, and yeah, this is by me, Michael Matsuda. So let's get started. Alright, so first we have to use Aufbau's diagram to write out the electron configuration of silver and molybdenum. So let's do that. First I gotta get the diagram up, so I'll do that right now. Alrighty, so now that we have our diagram here, we can start to fill it out with the elements. So let's start with molybdenum. Molybdenum. Denum? I'm not sure if I'm pronouncing that right. I'm sorry if I'm messing it up. But so right here we can see that the element molybdenum is 42. So that means it has 42 electrons. So we can use that information to fill out Aufbau's diagram right here. Oh, zoomed in a lot. All right. Ooh, it zoomed in again. I'm sorry. Anyways, so we can fill it out. Remember when you're filling it up to always fill out the lower orbitals first. So we're going to go to 42. Let me write that down. 42. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42. So, as you can see here, uh, it would, if we were to write it out like this, molybdenum would be equal to 1s squared, because there's 2 right here, 1s squared, 2s squared, 2p to the power of 6, 3s squared, 3p squared, no, not squared, sorry, 3p to the power of 6, 4s squared, 3d to the power of 10, let me erase this right here, 4s, 3d, oh, sorry, 3p to the power of 6, 5s to the power of 2, and 4d to the power of 4. So, I mean, if you look at this, it looks pretty fine, right? But actually, this is incorrect for molybdenum, and I'll explain that later. But first, before we do that, let's do silver. So silver, if we look at silver, silver up here is Ag, and that's 47. It's right here, 47. So we already know that it's 42 for molybdenum. So we can just add 5 more to that. So let me get my writing tool. So 42, 43, 44, 45, 46, 47. So basically, silver would be the same thing as this. It would look, or it would have the same numbers, but 4d would be 4 to the power of 9. So it would be 1s squared, 2s squared, 2p to the power of 6, 3s squared, 3p to the power of 6, 4s squared, 3d to the power of 10, 4p to the power of 6, 5s2, and 4d10. I mean, not 10, sorry. 4d9. To simplify these, because since they're pretty long, we can do, since there's the noble gases, right? And these noble gases have full full orbitals. So we can simplify all those numbers in the beginning. So since krypton right here is 36, we can simplify it. So everything before 3p, here, everything right here, I think it's right there. Wait, let me check for a second. Okay, yes, I was right. So everything under 5s can be all simplified. So all of these numbers can be simplified as just Kr for krypton. So I'm going to use that when I write it now. So basically, the second part, it says, explain why these configurations do not follow what would be predicted by the rules. So by the rules, it would look like these. These would be the answers. This one and this one. That's just how they would look. But actually, that's not how they are written. The real way that they are written looks something like this. So let me zoom out and move it over here a little bit. All right. So it would look a little something like this. So I'm going to put KR because I don't want to write that whole thing again. So then it's going to be krypton, sorry. And then it'll be 5, this is going to be for molybdenum. 5s1 4d5. And you may be wondering, why did I move the 5s from 2 to 1 and make the d that was 4 5? And that's because the electron orbitals are more stable, half full, than any other configuration, except for if they're fully full. So that's why this 5s right here, let me zoom in again. Let me get a different color. So this 5s right here, it had two, one right here and one right here. And this one right here only had 4. 1, 2, 3, 4. So since this is missing right here, it's missing one. To make it more stable, this donates one to this one so that they're both half full, and that'll make it more stable than if this one box was empty and this had 2. And also that's the same for silver. So silver would be written like KR5S1 4D10 because the 1 donates to the silver. I mean, the 1 in the 5s, one of the 5s orbit electrons donates to the 4D so that it becomes a full electron orbit, and the 5s is half because the half would be more stable than if it was just missing one. And so that would look like that, and then this would be missing that one. And this is all because it would just be more stable that way, and it will function better. And this property of sharing from the 5s to the 4 to the next d orbital, so it could be from the 4s. Oh wait, let me get to it. It could be from the 4s sharing to the 3d, or the 3s sharing to the 3p. Oh wait, no, it can't be from there. No. It can be from the 4s sharing to the 3d, 5s sharing from to the 4d, the 6s sharing for the 5d. It's all because the s orbitals are very close in energy level to the d orbitals, and that's why they can share. And you can see this sharing process usually happens within these elements right here. Within these elements right here, because they all are in that area where they can share from the s orbital to the d orbital. And yeah, that's basically it. Thanks for watching. See ya. Alright, just to recap a little bit, sorry this video is pretty long, but I know it was kind of, it might have been a little confusing for, I don't know. Anyways, so basically the silver and molybdenum are one of those elements that that really break Aufbau's rule, which is basically electrons occu occupy the orbitals of lowest energy first. And as you could see, they skip that by going up one to make it more stable. And really, yeah, that's just the property of the electron orbitals. And yeah, I hope you enjoyed this video, and thanks for watching. Bye bye.